Welcome back, everybody. This is Miss List, and this is 5.11, which is the last section of Unit 5, and it is on catalyst or catalysis. So a catalyst is a material that is used to speed up a chemical reaction but is not consumed by the reaction. We looked at these a little bit in an earlier section where we were discussing like the difference between a catalyst and an intermediate. A catalyst is something that gets added but then returned. So we can look at catalysts as working one of two ways. One is by changing the number of effective collisions. So we're making the collisions happen better, more effectively. Examples of that might be the catalyst provides a surface area for the collisions to happen on. The other way that a catalyst can be used is by altering the chemical pathway to one that requires less energy, especially for the rate determining step. So it can give a lower activation energy. We like to subdivide catalysts into two categories. One is a homogeneous catalyst, that's going to be in the same phase as the reactants and can mix with them uniformly. This is usually seen in gas phase reactions or aqueous phase. And then we also have a heterogeneous catalyst, which is a different phase from the reacting particles, such as I add a solid to an aqueous reactant. So one example of this would be the decomposition of hydrogen peroxide. This does happen naturally over time. You might have done this as the elephant's toothpaste. If you've ever done or seen this done before, this can be sped up because this is why like hydrogen peroxide stored in a brown bottle is because this process happens naturally and UV light speeds it up. So we put it in a brown bottle to block the light out. Well, we can actually make it go even faster by adding a catalyst. And sometimes that catalyst is solid Ki. So if I was doing this reaction in the lab, I can add solid Ki to this that is aqueous. And that's an example of a heterogeneous catalyst. I'm putting in something solid into an aqueous solution, and that is speeding up the reaction. And when it goes fast, we get all the bubbles from this oxygen gas being released. And that's what makes it, if you put dish soap in there, that's what it makes it look kind of like toothpaste. So let's look at each of these types a little bit in detail. So the homogeneous catalyst provides a different chemical pathway. And so this is one that is the same phase. And one way it does this is by providing maybe instead of one step, we might have two steps, or an intermediate is formed by adding that catalyst. So in our energy diagrams here, we have the uncatalyzed reaction is represented by this bold line, and they're showing one step. But if I add a catalyst, what that does is it provides an alternative pathway, and that's represented by this dashed line. And if you notice the activation energy here for the uncatalyzed versus the activation energy here for the catalyzed reaction, that makes the reaction go much faster because that is a lowering of the activation energy. So this is what happens when we have an example of homogeneous catalyst. So remember, again, this is going to be something that's the same phase. And this gets added to the solution and it provides an alternative pathway. So instead of having to go all the way up here and then down, we have a two-step mechanism with the catalyst, and the catalyst is probably going to form some intermediate, and then the products would be formed after that. On the right, we have the effective catalyst when it comes to our Maxwell-Boltzmann We've seen this guy come up again, Maxwell Boltzmann chart or graph. And without the catalyzed reaction, we're going to have an activation energy that is higher. And so that means only this shaded amount in red have enough energy to go to products. But when I catalyze the reaction, I'm essentially lowering the energy threshold. And so I'm going to see much more particles that have enough energy in order to go form products. A heterogeneous catalyst is something that works in a different phase of the reactants. And the way it speeds up the chemical reaction is usually by providing like a solid surface that helps the particles be oriented to each other properly. So in this diagram down here, we have one reactant gets absorbed to the surface of the catalyst. So this is my catalyst here. And what they're showing is that this would be a solid phase catalyst. That's kind of what they mean by these lines, is my solid phase catalyst. So the idea is that one of the reactants attaches to the solid, and this would be gas phase. Now, because it's attached, it's no longer bouncing around like we know gas particles to do, and that allows it to be oriented properly in order to receive the other reactant. And if that happens, then we can get the bond broken here and new bonds being formed, and then it will be released from the catalyst. So this is an example of a heterogeneous catalyst where it's providing a surface area for the reaction to happen in. In atmospheric chemistry, there is a lot of solid particles that catalyze reactions like this in the atmosphere. Things like dust, smog even, can provide surfaces, little particles, for things like ozone to attach and then break down. Well, that's not great because we don't want the ozone layer to go away. We want the ozone to stay. And so that having that catalyst in the atmosphere is actually really bad for us. And so that's why having a lot of smog and a lot of particulate matter that is in the atmosphere is such a bad thing for the ozone layer. That's something I studied when I was in grad school, so I just thought I would add that as like a real life application of a heterogeneous catalyst. Not all catalysts are good. In this case, that would be one that we don't want to have happen, and it would definitely be a negative. All right, guys, that is it for Unit 5. I thank you for sticking with this. You are more than halfway done. There are only 9 units, and you have 5 done, 4 left to go. I'll see you next time with Unit 6. Bye, y'all.